So next, let us see what is Boolean difference method in the VLSI testing. So as we have discussed different combinational ATPG algorithms. So we started with path sensitization method, that is PSM usually in short we call, and then we'll move on to the Boolean difference. So basically it is depending upon the Shannon's method. So if for a function f which consisting of x1, x2 and xn are the variables, and if you find out any variable substituting value as 1 and 0, so that is y is equal to 1 and y is equal to 0, substituting in that df by dxi, that is called as the Boolean difference of f with respect to y. So this Boolean difference method, we have already seen that how it is used to find out the transition density in the low power application. Now we'll see that how this Boolean difference method is used to detect the fault in the circuit. So when I perform the XOR operation of y is equal to 1 and 0, and if I get that equal to 1, it indicates that fault is detected. If it is 0, it means that the fault is not detected. In the sense, so if XOR operation is 1, that means we'll get the output of XOR gate as 1 if both the inputs are of different. So that means we are comparing fault free output and faulty output. If they are different, then we say that the fault is detected. Suppose the faulty output is equal to fault free output, then the XOR operation of fault free and faulty output becomes 0. So that indicates that even though we get the faulty output result, either it may be 0 or 1, if it is equal to fault free output, then that fault may not be seen at the output. So that's why we are finding out the XOR operation of substituting a value or any variable with respect to the output as 1 and 0, and then we'll find out if at all is equal to 1, that means the faulty output is different from the fault free, hence the fault is detected, or else it is considered as undetectable fault. So let us see with an example. So as you already aware that how to find out the faults in a given circuit. So just for an example, AND gate, you know that, so if there are two input we have and one output, so the total fault site in this two input AND gate is 3. So total stuck at faults are 3 into 2, that is 6. So those 6 are nothing but x stuck at 0, x stuck at 1, y stuck at 0, y stuck at 1. Similarly, output may be stuck at 0 and stuck at 1. So there are 6 faults which we can consider for the AND gate. So using Boolean difference, if at all I wanted to find out what is the test pattern to detect the fault. So let us find out how we can find out here. So as we know that a method or a general method, or it may be a PSM method, if at all x is stuck at 0, I need to excite the fault by assigning the opposite value, means I will be assigning x is equal to 1. So in order to propagate that fault to the output, the another input must be a non-controlling value, in the sense I need to make y is equal to 1, so that the fault which was there at x can be seen at the output z. So if x is stuck at 0, then the test pattern what we are able to find out, that is nothing but x equal to 1, y is equal to 1. So that is how we used to calculate. Similarly, using Boolean difference, let me assume that how that can be detected. So z is equal to x into y. Suppose if there is a fault at x, that means that is x is stuck at 0, then I will find out the Boolean difference of z with respect to x. That's why I will be writing dz by dx, that is nothing but substituting the value of x is equal to 1 XOR with substituting the value of x is equal to 1. I am equating that with 1. If I get 1, that means the fault can be detected. So now, so substituting x is equal to 0 in z, that means I will get 0, XOR with substituting x is equal to 1, I will get y. So XOR operation of 0 XOR with y, that is nothing but y. So in order to find out x stuck at 0, so I will be rewriting that as x into dz by dz, which is equal to 1, that is nothing but x into y, whatever I have got here, dz by dx as y. So the test pattern to detect, now I can say that x stuck at 0 is nothing but x and y, that is nothing but x is equal to 1, y is equal to 1. So that means using Boolean difference also we can find out what is a test pattern to detect the fault. Similarly, if x is 1, so what I will do, if x is equal to 1, again same thing, I need to find out dz by dx, which is equal to substituting the Boolean difference of f z with respect to x. So again we are getting y, but since I am finding out x stuck at 1, the equation becomes x bar into y. So x bar we need to substitute. Then the test pattern becomes 0, 1. So this is how the Boolean difference works. And as you know that this is another way in which we can find out the fault in a given circuit. So if at all we are following the Boolean difference method, the way in which you need to solve is you need to find out the Boolean difference and then substitute the equation in the form of which fault is detected by substituting that fault opposite value. Suppose if x is stuck at 0, you need to substitute x into the Boolean difference, and if x is stuck at 1, then x bar into Boolean difference of the particular expression what we are calculating. So just consider another example wherein the output is denoted with f. So f can be written as in terms of input, if I write it is xy plus y bar z, or else the intermediate nodes which are defined here is p and w. I can also write f is equal to p plus w. So the fault which we need to consider or which we need to find out here is say y. So it may be y stuck at 0 or stuck at 1. I need to find out using the Boolean difference. So that's why I will find out the Boolean difference by substituting y is equal to 1 and y is equal to 0 and performing the XOR operation of those two. So df by dy, and I will write the equation as substituting y is equal to 1 XOR with y substituting y is equal to 0. So for a given expression of f is equal to xy plus y bar z, substitute y is equal to 1, I will be getting f is equal to x. So here y is equal to 1 is 1 bar, this will go to 0. So I have f is equal to x. Similarly, substituting y is equal to 0, that means this term will go to 0. So I have 0 bar, that is 1 into z is z. So XOR operation of Boolean difference, what I am getting here is x and 0, that is z. So perform the XOR operation of x and XOR z. So how do you got x? We got x by substituting y is equal to 1 and we got z by substituting y is equal to 0. So when you perform the x XOR with z, so the expression which you can write here is x bar z plus x z bar. That means the Boolean difference of f with respect to y that we got as a XOR operation of x and z. Then, so since y is stuck at 0, I need to find out. I will be rewriting that expression as y into df by dy. So substitute the value of df by dy as x XOR with z. So I will be rewriting the expression as x bar yz plus xyz bar. So the test patterns are 0, 1, 1 and 1, 1, 0. These are the two test patterns which are able to detect y stuck at 0. Similarly, I can find out if y is stuck at 1. So if y is stuck at 1, I will just modify the expression as y bar into df by dy. So substituting the same df by dy as x XOR with z and keep in mind that now I have to substitute this as a y bar because I am finding out y stuck at 1. So the simplified expression what I will get here as x bar y bar z plus x y bar z bar. So that corresponding test patterns are 0 0 1 and 1 0 0. So using Boolean difference, so if there is a fault which is given here as y, that means it may be stuck at 0 or stuck at 1. The corresponding test patterns which we can use to detect here is 0 1 1 1 1 0 for y stuck at 0, and 0 0 1 and 1 0 0 is used to detect y stuck at 1. This is how the Boolean difference works. So let us just check with the another example wherein z is stuck at 0. So if z is stuck at 0, so if I find out the Boolean difference of f with respect to z and equating that equal to 1, so since it is a z is stuck at 0, I will be writing z into df by dz equal to 1. So I will be the expression what I can write here is f is equal to xy plus xyz. So substituting z is equal to 1, we are going to get that as xy, and substituting z is equal to 0, find out what is the expression. So you are getting xy XOR with xy. So after that what we are getting, the XOR operation of xy and xy is nothing but 0. So z into 0 is 0, which is not equal to 1. That indicates that this is a satisfiable, it is nothing but undetectable. That means the Boolean difference which is equated to 0 indicates that the faulty output is equal to fault free. So hence we are not able to detect the fault. So this is how we can prove it. So just take another example. So wherein I can consider the chain rule here. So because there may be internal nodes, under such case I can make use of the chain rule here. So you can see that to a stuck at 0, so through this path I have an intermediate node that is z. So if there is a fault at a, that means dz by dy I need to find out. So if there are multi levels we have, under such condition there may be a lot of expressions which we need to solve. That means we need to perform the XOR operation and so on. So that's why we can make use of something called as a chain rule, wherein to find out dz by dA, what I will do here, first I will find out dz by dz. That means dg is the intermediate node between a and z. So first I will find out the Boolean difference of dz and dg, and then I will find out dg by dA. So then I can find out dz by dA. So that is how that is called as a chain rule. So we can apply chain rule to find out for simplicity. So you can individually handle the variables with a small expression. Otherwise, so writing z in terms of all primary, the expression may become very large. So that's why what we are doing here is